Hello, what I've got is another video of the force of a current carrying wire on a current carrying loop. So magnetic force, magnetism, current, electricity, all that good stuff. So what we have is a current carrying wire, and then that current carrying wire is going to create a magnetic field around it. And so that magnetic field around it is now going to have a loop put in it. And because this loop is carrying a current itself, a current in a magnetic field has a force on it. So we want to know what is the net force on the loop. All right, so to begin with, I'm going to focus on I1 because that is the thing causing the magnetic field. So the magnetic field that we care about is caused by I1, so let's just start with that. Got current going this way, I1, and then imagine the loop here. We want to know what the magnetic field is from I1 at these two positions, where the loop is. But I'm not drawing the loop, I'm just going to focus on those two positions. And one is 5 centimeters down, and the other must be 5 plus 12, not to scale, 17 centimeters down. Okay, so let's go with direction first. So the direction of the magnetic field from a current carrying wire, that's right-hand rule number 1. Thumb in the direction of the current, the magnetic field curls in the direction of your fingers. So if this is the wire curling around, so the magnetic field is going like this. And that means on the bottom it's going into the page, and on the top it's coming out. So we have, okay, so into the page. Magnetic field here is into the page. All right, how big is that magnetic field? Well, we can calculate that. So let's do the magnetic field at those 2 points, at the 5, and then we'll do at the 17. Magnetic field equation, magnetic field from a current carrying wire, that equation, mu naught times the current that's causing the field, which is I1, so 1.5, over 2 pi times the distance away, and I want the 5 centimeters, convert to meters, 0.05. All right, so what do we have there? At 5 centimeters, I get 6 times 10 to the minus 6 Tesla, and the direction into the page. Great. And let's do the magnetic field at 17. That will be mu naught times, again, the current causing the magnetic field, 1.5, over 2 pi times the distance away, 0.17. Here, not as pretty of a number, 1.77 times 10 to the minus 6 Tesla. Again, into the page. All right, so now we know the magnetic field caused by this wire at this point and at this point. So now I'm going to redraw it. I'm going to get rid of the wire because I don't care about that anymore. It's done its job. All we care about now is that we have this magnetic field. It's into the page, and then we're going to put a loop into it. And we've got 12 centimeters this way. Okay. And what direction is the current? I'm going down there and up there. Okay. Now, this side, the perpendicular pieces, we don't care about. The forces from these are going to be 0. All we care about is the force from the top bit and the force from the bottom bit. If you want to be formal about it, you can say the force left is 0, force right is 0, and we just care about F top and F bottom. So let's figure out what these two are. What is the force on the top bit of wire? Okay, so the force on this top bit of wire, the equation is ILB sine theta. We're ignoring the sine theta. It's always going to be 1 for our problems. So ILB. Current is the current that's flowing, which means 0.75. L is the length of wire that is in the magnetic field. I'm going to guess it's a square, Yeah, my actual problem says square. Good. So 12 centimeters, 0.12 meters, times the B field at that point. Well, what is the B field for the top bit of wire? That was the B field at 5 centimeters. So that's this one. 6 times 10 to the minus 6. Okay. And if we calculate that out, 5.4 times 10 to the minus 7 newtons. What direction is it? It's a vector, it's a force. So here's my little shortcut. I do I and B and then figure out what F is. The current in the top is going to the left. The B field that it's in is into the page. So what's the direction of the force? Okay, flat hand, current, and then I'm going to cross my fingers from I into B, downwards. Okay, and then I'm running out of room. Force on the bottom bit of wire. The current that's in this loop, which is 0.75 again. The size of the bit of wire we're interested in, 0.12. And now the magnetic field that this wire feels, which is that one, 1.77 times 10 to the minus 6. And calculate that out. We get 1.6 times 10 to the minus 7 newtons. What direction? Well, now the current is going to the right. The B field is still into the page. So the direction of the force, well, I mean, it's going to be opposite this, but let's just do it. So current going to the right, flat hand to the right, and then we curl our fingers to B. Thumb is pointing up, force is pointing up. All right, not done yet. One more step. We got one more step because we want the net force. And that just means we have to say, okay, here's one force that's going down, here's one force that's going up, add them. So that's bigger, so 5.4 minus 1.6 because opposite directions. So if we do that, the net force on the loop is equal to, well, we get 3.8 times 10 to the minus 7 newtons. Don't stop there, force is a vector, and which one was bigger? The down or the up? The up, what was that? Yep. No. There we go. Those two numbers. I'm like, which numbers am I looking at? That's bigger. So the down is bigger. This is an overall force downward. That is the answer I'm looking for. So there's our process. Figure out what the magnetic field is from this long wire. And we've got that. And now ignore that. Just deal with the loop in a magnetic field and figure out the forces, and you can get the net force. All right, hope this helps. Good job for watching.